In this segment, we consider another problem, that of authorship attribution. In authorship attribution, we want to determine who wrote a given text based on the signature word adjacency networks. In word adjacency networks, or WANs for short, function words are nodes, co-occurrence of these words define edge weights, and the word frequencies are graph signals. We will use GNNs to learn the authorship of short and attributed texts, leveraging the structural information provided by the WANs. Consider function words, which are those words that don't carry meaning. Their use depends on the language's grammar. Examples include adjectives and adverbs. Linguists have found that different authors use slightly different grammar, and, as it happens, we can capture these stylistic signatures by means of a word adjacency network, or WAN for short. The function words become the nodes of the WAN, and the edges measure the co-occurrence of each pair of function words. Pairs of words that an author uses very often will have a stronger edge weight than those pairs of words rarely used. In short, WANs measure how often pairs of words appear together. The fact that different authors use different pairs of words leads to different WANs for different authors. Here we see the one for William Shakespeare on the left, and the one for Christopher Marlowe on the right. We see that these WANs are sufficiently different to ascertain their collaboration on the play Henry VI. Specifically, in the play Henry VI, there were acts written by Shakespeare and acts written by Marlowe, showing that it was not all written by Shakespeare as was once thought. Building WANs that accurately reflect an author's signature requires long texts. Thus, attributing short text becomes challenging, even if we have an existing accurate WAN. In a graph signal processing context, the WAN establishes the graph structure S, where nodes are words and edges reflect co-occurrence of pairs of words. The graph signal X is defined on the nodes, which are words. Thus, we use a word count of the short text to build a histogram of function words, and this is what we will use as a graph signal X. We can then use GNNs to classify the authorship of a short text, leveraging a given accurate WAN S and using a word histogram X of the short text to classify. For the numerical results, we consider two authors, Jane Austen and Edgar Allan Poe. We use a big portion of the corpus written by each author to accurately build the WAN S. The remaining texts, we use them as test set, and we split the text in short pages of around 1,000 words. We add to the mix other short text written from a pool of 22 contemporary authors. We compute the word count of function words on each page to build a histogram, which we use as the graph signal X. We will compare GNNs with different values of k, showing how words related beyond direct co-occurrence affect the classification performance. We also compare with a linear graph filter. On the left, we see the bar plot where we try to classify whether a page was written by Jane Austen or not. We first see that all GNNs outperform the linear filter. We also see that the best performing GNN is that for just 2 filter tabs, suggesting that the direct co-occurrence of words is good enough information to determine authorship, as was expected. On the right, we see the bar plot for classification of pages written by Edgar Allan Poe. We see, again, that the use of linear filters lags behind in performance. The best performing GNN is, again, that with k equal 2, arriving to the same conclusion that no information contained beyond direct co-occurrence is relevant in attributing authorship. This concludes the use of GNNs for authorship attribution of short texts. In this example, we use word adjacency networks as graph supports and word frequency histograms as graph signals. The GNN was used to learn a map between the histogram and the author, leveraging the word adjacency network.